All right, hello everybody. So welcome back after the guest lecture. I know it was a bit technical, but I hope people enjoyed it. Don't worry, there won't be any homeworks related to that lecture or any other thing that's well, there are no exams in this course anyway, but you're not going to be quizzed or in any way on the contents of that. That was just for fun. So thinking about what we did in the recent past, we've done a lot of stuff on norm estimation and embeddings, the Johnson-Lehmann-Strauss lemma followed by AMS sketch, Johnson-Lehmann-Strauss lemma, LP norm estimation, and then sketching for arbitrary norms and the relation to embeddings. Today we're going to stick with embeddings and we're going to talk about lower bounds. So today I'm going to show you an optimal lower bound for the Johnson-Lehmann-Strauss lemma. Right. So we know from JL that any endpoint subset of Euclidean space embeds into m-dimensional Euclidean space with distortion 1 plus epsilon, where m is O of 1 over epsilon squared log n. And I haven't defined, I don't think I've used some of these terms, like what does distortion mean? Basically, distortion means, if you have two metric spaces, let's say I have a metric space, x with distance function dx and y with distance function dy. These are two metric spaces. And then you also have a function f which maps x to y. Then if it's so rho, basically the distortion rho, or actually I should say it's at least okay. It's true that it's at least one, is the smallest value such that there exists, or the distortion rho of f is the smallest value such that there exists some scaling constant c such that for all points x, y in capital X, if you look at the distance between the distance in y between f of x and f of y is at most rho c times the distance in x between x and y. It's at least c times the distance in x and y. This scaling c business only matters for kind of non-normed spaces. In normed spaces, usually the question we're interested in is, does there exist an embedding of low distortion, right? So for that, you don't really need this C there, because if you have something that has the C, you can just take the embedding and scale it by 1 over C, and then you'll just have D on the left and rho times D on the right. But you can do that in normed spaces. You can't necessarily do that in arbitrary metric spaces. But we're just dealing with norm spaces here anyway. We're dealing with Euclidean space. So right, so you could ask the question of, JL gets this distortion 1 plus epsilon with target dimension 1 over epsilon squared log n. Is that the best possible? Is the JL lemma the best possible? Or is it true that, so really the question is, does there exist a bad point set such that for that point set, you can, for every epsilon, let's say, and for every n, does there exist a bad point set with n points such that you cannot do better than JL if you want distortion 1 plus epsilon on those endpoints? And it turns out that the answer is yes, JL is the best possible. And the history of what was shown is as follows. So first we have in 1984, the JL paper itself showed that if epsilon is smaller than some constant, like a third or something, actually, we'll see. Well, I'll show you this argument. And some fixed constant, say a third. It's not exactly a third. Then there exist point sets that require target dimension to be at least some constant times log n. So that argument is not sensitive to epsilon. Kind of, once epsilon is less than a third, you just get a lower bound of log n. If epsilon is 0.001, you still just get a lower bound of log n. It doesn't capture the hardness that comes from the epsilon. And then Noga alone, for the year, so there's a 2003. Showed that there exist point sets that require m to be at least 1 over epsilon squared log n over log 1 over epsilon. So this is optimal except for that, it doesn't match, the JL upper bound does not have that log 1 over epsilon in the denominator. And I should really mention that the lower bound is like the min of this quantity and n and d, right? Because you're never going to prove a lower bound better than d, right? D is the original dimension. You're never going to prove that there's a lower bound better than d. Why? Because there's always an embedding into dimension d with distortion 1, with no distortion, namely the identity map, right? Just take the points themselves. You're also never going to get a lower bound better than n minus 1. And why is that? So take your endpoints. You can translate them. If you translate all the points by the same amount, the distances don't change. So translate them so that one of them gets moved to 0. Okay. Now you have n minus 1 points together with 0. These n minus 1 points with 0 span a subspace of Rd of dimension at most n minus 1. Okay. So since they're in an n minus 1 dimensional subspace, you can embed them in dimension n minus 1 and preserve all the distances exactly. Right? Basically just rotate the subspace so that it becomes the span of E1 up to En minus 1 or something. Okay, so you're never going to prove a lower bound better than the min of n and d. So you can think whenever I write these lower bounds, what I mean is, m is the min of n, d, and this quantity is lower bound. Okay. My pencil likes to change itself to eraser by itself, has a mind of its own. In 2016, there was a lower bound by Casper, Green, Larson, and myself that showed that m is at least 1 over epsilon squared log n for linear maps. Right. So if you look at the JL lemma, what are we trying to do? We're trying to embed d-dimensional Euclidean space into 1 over epsilon squared into lower dimensional Euclidean space. Now, the JL lemma just proves the existence of such a map. It turns out that in the proof, this map is a linear map. X gets mapped to A times X for some matrix A. Okay. So in this paper, what we proved was that there are point sets such that if you insist on the embedding being a linear map, then even if it's not random projection, you're allowed to do whatever fancy linear map you want. There simply does not exist a linear map that does better than JL. Okay. But for our hard point set in that work, potentially actually there was a nonlinear map that actually did better than JL for that point set. So we really crucially used the fact that the lower bound was only against linear maps. And then the thing I'm going to show you today is also with Casper, Green, Larson, and myself, is that m has to be at least 1 over epsilon squared log n. Okay, so and and this is a lower bound against any map. So even if you allow yourself a nonlinear embedding, you still can't do any better. And interestingly, it doesn't. I mean, you're going to see the proof today. It doesn't use any tools that I feel like. Well, okay, so it does use some language that I will have to introduce, but the basic idea is an idea you've already seen in our previous discussion of lower bounds, right? So I thought, how did we come up with lower bounds before? There were compression arguments and there were communication complexity arguments, the latter of which often you prove the communication lower bound itself via a compression argument. But it's going to be the same kind of thing. It's going to be a compression argument. We're going to show you today that, basically, I don't know a specific point set for which you can't beat JL. But what I can do is I can define a very large collection of point sets, so a set of point sets, such that, if for every point set in that collection you can beat JL, if that is true, then I can use that fact in a black box way to define an injection from that collection of point sets into a smaller set, which is a contradiction, right? I can't have an injection from a big set into a smaller set. Therefore, the assumption that every one of these point sets has a good low distortion embedding that beats JL is not true. At least one of the point sets in that collection, you cannot beat JL. Again, that's open, which, tell me an explicit point set. Tell me one point set where you can't beat JL. I have no idea. But I can tell you a large collection of point sets for which one of them I know you can't beat JL. Okay, so let's start off with the original lower bound of JL, because it uses ideas actually that, that get used in the very last, the optimal lower bound. So Nogo Alone, when he came along, he gave an argument that was totally different from the original JL argument. And then the 2016 paper was also different from JL and from Nogo Alone, completely different. And then the 2017 optimal lower bound actually went back to the language of the original JL lower bound. I mean, of course, you had to do some more work because you're proving a better bound, but I would say it was in the same category of proofs, sort of. So JL 84 lower bound was what's called a volumetric argument. So they look at the hard set of points. Capital X for them is, say, 0, 1, the 0 vector together with E1, E2 up to, let's say, En minus, or En. So it's a set of n plus 1 points. So pretend n was actually n plus 1. Or just drop the En, it doesn't matter. Now, say I have a low distortion embedding F, which maps X into Rm. I can translate so that f of 0 is 0, right? Again, if you translate, basically translate everyone by f of 0. Okay. That doesn't change pairwise distances. Okay. So, and let's also say define ei tilde to be f of ei. Right, if in case you don't remember, ei is just the standard basis vector, right? So ei is the vector 0, 0, 0, and then a 1 in the ith position. 0, 0, right? This is ei, the simplex. Okay, so what's the picture here? So here's the picture. Originally, all the EIs, have unit norm, and their pairwise distances are the square root of 2. Okay. Now, after you map by f, you know that, first of all, that for all I, if you look at the distance between f of ei and f of 0, this is the same thing as the distance from ei tilde to what is f of 0? F of 0 is 0. So that's just the norm of ei tilde. This had better be 1 plus or minus epsilon, right? Because remember, the distance to 0 is preserved. Well, the original distance to 0 was 1, so the new distance to 0 had better be 1 plus or minus epsilon. Okay. So here's the picture. Here I have a ball of radius 1 plus epsilon. And this is, in our M. What do I know? I know that all the ei tildes are in this ball because they all have norm at most. They all have norm that's 1 plus or minus epsilon. What else do I know? I know that if you take 2 of them, so here's some ei tilde. Here's some ej tilde. Okay. They have to be far apart, right? Because originally their distance was root 2. So now their distance has to be at least, for all I not equal to j, I know that the distance from ei tilde to ej tilde has to be at least 1 minus epsilon times the square root of 2. Are they also outside the ball of radius 1 minus epsilon? Sorry, can you rephrase the question? No, I didn't quite understand what you mean by that.
Or like if the norm has to be like less than 1 plus epsilon, but also has to be greater than 1 minus epsilon. So it's going to be
right.
like a thin shell.
That's right. And yeah, so I'm not going to use, that's true. I'm not going to use that fact, but what you're saying is correct, that they can't be toward the origin. They have to be kind of near the boundary because their norm is also at least 1 minus epsilon. That's true. Okay, so I know that these things are far apart, which means if you take balls around them, let's make this ball red. These red balls have radius less than, say, 1 minus epsilon root 2 over 2. Let's call this r. So this is radius r. This is radius r. These balls have to be disjoint, right? Because if they were not disjoint, there's some point in the that's common in the intersection. Let's call that point x. Then by triangle inequality, right, I could go from ei tilde to x, and from x to ej tilde, I would have a path of length at most 2r between them, which means the distance between them is at most 2r. But I know that's not true. I know their distance is more than 2r, right? Or it's at least 2r. So all these balls are disjoint. So let me draw them. There are a bunch of them. How many of these balls are there? There are n of them because there are n ei tildes, right? So there are these n red balls, and I know that they're all disjoint. But all these balls are contained in a bigger ball. Right? This yellow ball here, this, let's say, so what do I know? I know that ei tilde has norm at most 1 plus epsilon. And then this ball has a radius of 1 minus epsilon root 2. So this has, let's say, radius of 1 plus epsilon plus 1 minus epsilon, root 2, right? Which it's roughly 1 plus root 2, which is less than 3, anyway. If epsilon is smaller than a third or something, this is less than 3. So what do I have? I have n balls of a certain radius that are disjoint, and they're all contained in a radius 3 ball. And now I can end the argument. How do I end the argument? The volume of the union of the red balls, okay, is equal to the sum over the red balls of the volume of that red ball. Right? This is because the balls are disjoint. Right? Since the balls are disjoint, the volume of the union is the sum of the volumes. On the other hand, I also know that the volume of the union of the red balls, well, the union of the red balls is contained in the yellow ball. So this is at most the volume of the yellow ball. Does that make sense? And also I know that, all these red balls are the same, right? They all have the same radius, so they all have the same volume. So this is just equal to n times the volume of a red ball. And let me say also, so I said those red balls have radius r, and let's say this yellow ball has some radius r prime. So just rearranging things, what do I have? I have that my inequality is that the volume of the yellow ball divided by the volume of the red ball is at least n. Does that make sense? Right? Are people with me? Any questions?
Looks good.
Okay. And now what is that ratio? I mean, you can look it up, what is the volume of a ball in, an m-dimensional space, a Euclidean ball? It doesn't really matter because the point is it's going to cancel. So the point is, if you have a radius r ball in dimension m, the volume is going to be something like r to the m times something that depends on m that, you can look up what the volume of a ball is. But the point is, so the numerator is going to be like r prime to the m times blah. The denominator is going to be r to the m times blah. So this ratio is going to be r divided by r prime to the m, which implies that m is omega log base r divided by r prime of m.
Should it be r prime over r?
Yes, that's correct. And, you just look at what we have here, and, r prime and r are both constants. R prime divided by r is some constant. So you have log base some constant of n. So it's omega log n. And you can see here why this argument is not so sensitive to epsilon. Basically, I mean, what do you know? You know that, so what can I say here? R prime over r, so you want to minimize the base of the logarithm, right? Because log base 1,000,000 of n is a smaller lower bound than log base 2 of n. So the smaller you can get the base, the better of the logarithm. On the other hand, you know that you're never going to be able to get r to be bigger than r prime over 2, right? Because you have at least two red balls that are completely disjoint inside this yellow ball. Each of those has radius r, therefore the yellow ball can't have radius. Therefore, r can't be more than half the radius of the yellow ball. So you're never going to get better than log base 2 of n. And this argument maybe is going to get you something close to log base 3 over root 2. So it's, I don't know, log base 5 of n, log base 6 of n. So you're getting within some constant of that. But even if you try to incorporate epsilon in your arguments, there's some limit as to what the base of the logarithm is going to be. Okay. So that's it. That's the JL lower bound.
Well, how do we get the 1 minus epsilon root 2 for each EI tilde being far apart from the other EJ tildes?
How do you know that they're far apart?
Yeah. Or by 1 minus epsilon root 2.
Well, because EI in the original space, EI and EJ has distance root 2, right? EI is the vector that has a 1 in the ith position and a 0 everywhere else. So if you look at EI minus EJ, it has a 1 somewhere and has a minus 1 somewhere. The norm is root 2. And my assumption was that F is a low distortion embedding. It preserves all the distances up to 1 plus or minus epsilon. Therefore, the distance between EI tilde and EJ tilde, which are the embedded versions of EI and EJ, have to have distance at least 1 minus epsilon root 2, right? So if you have 2 points that are at distance at least, d, then the balls of radius d over 2 around them have to be disjoint. If not, there'd be something in the intersection, and by triangle inequality, they'd be closer than d, which is not the case. Does that answer your question?
Yeah.
Okay. So that's the JL lower bound.
Professor, can I ask a question?
Yeah.
The JL lower bound, and specifically in this case, like it's hold true for all point sets. In this case, we use like a well-separated set. So are there conditions on like the point set in which we can sort of exceed the lower bound?
Wait, is there like, are you asking if whether there's a characterization of point sets where you cannot exceed the lower bound?
Yeah, it seems like, because in our counterexample, we used a really well-separated one, right? Is that like a hard, like it's just like a particularly hard problem to have low distortion in?
Right. Well, I mean, I guess as you see from the argument, as you're right. The only properties we used about the EIs and EJs, I mean, we used the fact that they had some bounded norm to say that everything fits in the yellow ball. And we also use the fact that they're well separated in the original space, so say that they're still going to be well separated in the target space. So you would get the same lower bound using any such set. It doesn't have to be the EIs and EJ. It doesn't have to be the simplex.
I guess my question is, if we knew some property of a point set that they're not well separated, can we exceed the JL lower bound?
Yeah. So what you can do is, I'll say the following. So JL says like you can get M to be O of log squared n over epsilon log n. Sorry. Log n over epsilon squared. There's a theorem of Gordon from '88 that says the following. So let's say that your x has size n here, and let's define T to be the set of all normalized difference vectors. So x minus y divided by the norm of x minus the norm of y for all x not equal to y in capital X. And then there's something called the Gaussian mean width of T. Let me not use the same thing twice. So let's call it width for W for width. W of T is defined to be the expectation over a Gaussian vector. So G is distributed, GI are IID normals, mean 0, variance 1, of the sup over x and t of G dot x. This is called the Gaussian mean width. And Gordon said that it's enough to choose M to be big O of the squared width of T, let's say plus y over epsilon squared. So, yeah, this is some, it's more, yeah, so this is some notion of easiness for JL in the sense that, if your point sets are nice, then somehow you can do better than JL. You can prove that W squared of T is never bigger than log n or O of log n. So this is never worse than the JL bound, but sometimes it's better. And kind of the hard case here is really when the vectors in T, so forget about X for a second, let's just look at T, which is the normalized difference vectors. The hard set is the case when the vectors in T are all orthogonal, which basically, I mean, that's not exactly the same as the simplex, but those vectors are not all orthogonal, but that is the hardest set. Notice though that the simplex, I mean, it does contain a large subset of orthogonal vectors because you have 0 in there and then you have the EIs. So if you look at EI minus 0 over the norm of EI minus 0, that itself is the simplex again. So T contains the simplex plus some other and choose 2 other things too. So that simplex that it contains is kind of why it's hard. But the cases that are easier are like basically where, let me draw T. So if T looks something like the following, where there are like all these different, there might be a lot of vectors, but they're like clustered. So imagine like this is T, right? Then as these clusters become like arbitrarily small, kind of the mean width of T starts looking more and more like square root log the number of clusters. It's not exactly, yeah, so it's not exactly that because, yeah, well, okay. But anyway, I mean, the easier case is when the T is clustered. The harder case is when T has a bunch of orthogonal vectors. That's something that's known. I don't know if we're going to have a chance to prove Gordon's theorem in this class. We'll see where we get, but does that help answer your question?
Yeah. So if like Gordon had a matching lower bound, then it would be like a strictly better, like more adaptive statement than like JL, right?
Yeah, unfortunately, there's no lower bound saying that this Gordon bound is optimal. Like there are, it's not a characterization. It's not like for every point set, the exact right answer is W squared T over epsilon squared. That's not true.
I see.
There are point sets where you can do much better than Gordon. And maybe you need to do a nonlinear embedding to do better than Gordon. The Gordon embedding is the same. It's just pick a matrix of random plus minus ones or random Gaussians. It's the same random projection thing.
Okay, thanks.
This is a better analysis of random projections. Okay, so let's get to one more thing that I wanted to add maybe to history is there was something in 2011 and there were 2 papers. One was by J-Ram and Woodruff. And there's another paper by Kane, Mecca, and myself. That what that said is that the distributional JL lemma is optimal. Right, so remember distributional JL. Distributional JL says for all epsilon delta, there exists this distribution d epsilon delta over matrices such that for all x in RD, the probability over choosing a random matrix from that distribution that you fail to preserve it, is at most delta. Right, so the way that we proved JL in this class was, and the way that everyone proves JL, it's the only proof of JL that we know, was pick a random, first of all, you show that such distributions exist. Oh, and also I should say, here M was like 1 over epsilon squared log 1 over delta, right? So you show that this distribution exists. And then to get JL, you pick a random such matrix pi, you're embedding f of x is just pi x, and you do some union bound and you show that, if delta is less than 1 over n squared or 1 over n choose 2, then the union bound can go through and such a map exists. Okay. So in 2011, it was shown that this bound M for DJL, this bound, oops, that this bound is optimal. But that doesn't necessarily mean that JL is optimal, right? Because this is saying that if you insist on proving JL using DJL, then you're never going to do better than 1 epsilon squared log n. But maybe in principle, maybe there's some other proof of JL that doesn't use DJL at all and gets a strictly better bound, right? So that was kind of the state of affairs 2011, 9 years ago. And I think, I do have some time. Let me show you I mean, it's a useful thing to know about. I'm not going to show you the details of the proof, but how do you prove that DJL is optimal? So, you say something like this. You say, look, for all x, and I'll show you the proof from Kane, Mecca, and myself in 2011. The J-Ram-Woodruff proof was actually different based on communication complexity. But you say something like this. Let's say you say for all x in RD, the probability over, let's say that you had such a distribution for DJL. You had this distribution d epsilon delta. So that means that for all x, the probability of a random matrix pi from that distribution, that pi x L2 norm squared minus 1 is bigger than epsilon is like minus delta. Well, if it's true for all x, then it's certainly also true for a random x. So let's say this implies that the probability over x coming from some distribution, let's call that distribution b, or the probability over pi of that same thing is less than delta. This is true for any distribution b. And then now I can change the order of the probabilities. So this implies that the probability over pi, probability over x of that thing is less than delta. Okay. So now what this is saying is for a random pi works for all but a delta fraction of the x's. And by delta fraction, I mean under the weighting given by distribution b, under the probability, delta fraction of probability mass under distribution b. Okay. So a random pi works for all but a delta fraction. So there must be some pi that does at least as well as the average. The average pi works for all but a delta fraction, so there must be some particular pi that works for all but a delta fraction. So this implies that there exists some pi star, which is an m by d matrix, such that the probability over x coming from b, that pi star x L2 norm squared minus 1 is bigger than epsilon is less than delta. And then you just show that no such pi star can exist if m is too small for a certain hard distribution b. So you say the hard distribution b is just uniform on the sphere. And then you show that this just requires some calculations that show that no such pi star can exist for this b unless m is sufficiently large. And sufficiently large basically means matches the DJL lower bound, or the min of that in D. And just some, this technique of basically this right here, this implication, going from like saying that's there has to be exist this pi star. I mean, this is called the easy part, the easy direction of something called Yau's minimax principle. I don't think you're ever going to see that term again in this course. I'm just saying it so that at some point in the future, if you ever see the term Yau's minimax principle, you'll be like, oh, I've seen that before when I took Jelani's course, years ago. Good. Okay, so that's all I want to say about the optimal DJL lower bound. It basically does this sequence of steps, and then it does some calculations to show that a short matrix cannot do well on the uniform distribution. Okay, good. So now the optimal JL lower bound. And before I can show you the optimal JL lower bound, there's just a few more kind of preliminary definitions that I need to give you. First, a primer on some convex geometry. So definition a convex body is a compact convex subset of RD. Okay, so convex, if you don't know what any of these terms mean, convex just means, if you look at the body, if you take any 2 points in it, and you look at the line between those 2 points, the line is not allowed to leave the body. So in particular, I think this might not be convex, because if you look at maybe this point and this point, that line does seem to leave the body a little bit. And then compact, it has a more general definition. I mean, I'm not assuming that people here have taken analysis or topology, but it does have a more general definition in terms of something called open sets. But for us in RD, it's just the same thing as closed and bounded. Maybe you know what bounded means. Bounded just means what you think it means. It's in a bounding box. It doesn't go off to infinity. Closed means that it doesn't have any so-called limit points which are not in the set. So for example, imagine, so closed means, contains all limit points. So for example, if you just look at the line from 0 to 1, look at the interval, 0, 1. So it contains 0, but it doesn't contain 1. So let's, sorry, I know for some of you I'm saying things, some of you maybe you're not familiar with these terms, some of you, you've seen this a long time ago. Right, so this half open interval is not closed. Why? 1 is a limit point. What does it mean to be a limit point? Being a limit point means, so 1 is a limit point because if you take arbitrarily small balls, arbitrary small intervals around 1, there's no way to do that without intersecting the set. So like the set is the set is S, right? So this is S. If you take an arbitrarily small ball or an arbitrarily small interval around 1, no matter how small you make it, any interval around 1 is going to intersect S. That is the definition of a limit point. So we'll say that 1 is a limit point of S. However, 1 is not in S in this example. So S is not closed. A closed set is a set that contains all its limit points. But if you took the closed interval that actually contained 1, then the closed interval does contain all its limit points. Okay, so this would be a closed set. So convex bodies are closed and bounded. So like this is a convex body in R2. This is a convex body, that's a convex body, etc. That's what you think. Okay, so just think polytope in some maybe high dimension. And a convex body, oh, and I should say it's a convex set of RD and with non-empty interior. So if I just have a singleton point, for example, or if I have a line in 3 dimensions, I'm not going to call that a convex body. It has to have some volume for me to call it a convex body. Okay. And a convex body is symmetric if, let's call it K, is symmetric if X in K implies that minus X is in K, just like coordinate-wise negation. In particular, notice that a symmetric convex body has to contain the origin. It has to contain 0. Why? Because since it has non-empty interior, there's some X in that body. And then minus X has to be in the body. And then the line from X to minus X has to fully be in the body because it's convex. And the line from X to minus X contains 0. It's halfway through the line. So, okay. And then now, a fact, which I'm not going to prove, is that symmetric convex bodies are basically the same thing as norms. Okay. So for every norm, that norm defines a body, a symmetric convex body, and for every symmetric convex body, that thing defines a norm. These two things are equivalent. So whenever you want to tell me about a norm, you can tell me it by, for example, telling what the body is. So why is that? So if I have a symmetric convex body K, I can define a norm. I'll call it norm sub K, where the norm of X is basically the largest element in the following set. It's the largest T such that Tx is in the body. So what, I mean, for example, like, what is the body associated with Euclidean space? It's a sphere, right? So in like dimension 2, the symmetric convex body associated with Euclidean norm in 2 dimensions is a circle. It's a circle of radius 1, right? So example.
Should it not be like T such that X over T is in K? It seems like if you scaled up X, then the soup would get lower.
Oh yeah, maybe you're right. Yeah, I think you're right actually. It's X over T. So let's think about it. So here we have this circle. That's not a perfect circle, I'm sorry. And then now let's say we have the point, we have a point out here, X, which has, it has norm 1.5.
Jeremy?
Right? Yeah.
So shouldn't it be like the smallest t, so like the infimum?
The smallest t. Oh, yeah. So I divided, I took soup instead of inf and I multiplied instead of divided. I think that is right. In particular, like I could set t to be, yeah. It made sense to say soup when it was multiplied, which was a bug. Now that I'm dividing, it should definitely be inf, right? Because I can divide by t being like infinity, and that's going to go to the origin. That's definitely going to be in k. So now that I'm dividing, it should be the inf. That's right. Right. So yeah. So the point is, okay. So I have this vector x here. If I wanted to stay inside the circle, I need to divide by 1.5 or more. If I divide by 1.5 or more, I will get mapped into the circle. So since the smallest number I can divide by to make it work is 1.5, I'll say the norm is 1.5. Does that make sense? Okay. And then, on the flip side, if I have a norm, I can define the convex body K, which is defined to be basically the set of all X that have norm at most 1. Okay. So I mean, this is how from Euclidean norm I get the circle, for example. L infinity norm, I would get a square. Right? I would get in high dimensions, I would get a box with side length 2, basically, because it goes from -1 to 1 in each dimension. Okay. Any questions about any of this? Okay. And now that you are experts in convex geometry, I'll do one more definition. If you have X, D is a metric space, and T is a subset of X, we'll say T prime is an epsilon net of T if for all X and T there exists an X prime and T prime such that the distance from x to x prime is at most epsilon. And then there's the entropy number, so-called entropy number n t d epsilon is the size of the smallest epsilon net of t under metric d. Okay, so a picture there, let's put it here, a picture there. I mean, let's just say that x is the real line, and let's say that, you know, the distance between x and y is just the absolute value, x minus y, on x, which is r. And let's let t just be the interval from 0 to 1. Yeah, I thought I fixed this bug of phone numbers showing up on my iPad, but I guess not. Okay. So what is a good, what's the best epsilon net? I mean, you basically just place a grid on this thing where, you know, you take the point at epsilon, you take the point at 2 epsilon, you take the point at 3 epsilon, all the way up to the point kind of 1 minus epsilon, I guess. And, you know, these red points are an epsilon net, and they're basically the best you can do, right? So, you know, question?
You're not space it out by 2 epsilon, because then each point could go to the left or right to get one that's within epsilon.
Oh, actually, yeah, that's a good point. I guess the first one would have to be epsilon. Okay, so yeah, maybe you're right. But I guess, okay, so I'll just be a little sloppy and I'll just say this thing. In this case, now I'm getting my notation all confused. N of, let's say, you know, 0, 1, where this is like just absolute value, I'll call it epsilon, is, you know, it's some theta of 1 over epsilon anyway. Yeah, maybe you can do what you said and save a factor too. Okay. Okay, good. And now maybe I want to do one more preliminary thing before I finally show you the proof, which is that there's this kind of duality between packing and covering. So I can define also, so I defined what n means. Let me define a packing number. The packing number let's call it P of TD epsilon, is the maximum number of pairwise disjoint balls under the metric D of radius epsilon that we can pack in T. So for example, imagine that T is like the circle of radius 1, and D is also Euclidean space, and then epsilon is whatever it is. Epsilon is some small thing. So what we're asking here is kind of what's the most number of small circles you can pack into big circle, such that, you know, the red circle, such that they're disjoint. And the centers have to be inside the black circle, but, you know, they might go out of the circle as long as the centers are inside. Okay. Does that make sense? This is the packing number. Okay. And now I claim that if you look at n, let's call it T well, let me be a little more, specific. So let's look at the ball of some norm. Okay. And let's try to get an epsilon net of it, in its own norm. Okay. So this is not necessarily a Euclidean norm, it's an arbitrary norm of radius epsilon. I claim that this is at most the packing number of the ball under that thing with radius epsilon over 2. Okay. So why is that true? So the proof of that is, so let's take, let's take that ball. Let's pack as many radius epsilon over 2 balls as we can. Take a maximal packing, etc. Each one of these has radius epsilon over 2. So we've packed as many as we possibly can, which means, if we take any other point that's not in a ball, like this point, why did we not put a ball around it? We didn't put a ball around it because the radius epsilon 2 ball around it intersected some other ball. It violated the packing condition of disjointness. Okay. Now take all these centers that did have balls, so all these centers, and expand them to have radius epsilon balls. So take those same centers and just have radius epsilon balls. And the claim is that these balls, these green balls, cover all of B by the triangle inequality. Okay. Right, so why? Pretend that there's some point in the ball, in the big ball, the black ball, pretend there's some point that's not covered by any green balls. If it's not covered by any green balls, its distance from every single red point is more than epsilon. Which means if you draw a ball around it of radius epsilon over 2, that ball doesn't intersect any of the other radius epsilon over 2 balls around. It doesn't intersect any of those red balls, right? If it did, then it would be within epsilon of that center by triangle inequality. Okay. But so then this point that's not covered by a green ball, you could have drawn one more red ball around it, but that's violates the optimality of your packing, right? P is the maximum number of balls you could have drawn, so you can't draw any more balls. And why is this a useful claim? It's a useful claim because now, how do you bound this thing? How do you bound the packing number? You can bound via a volumetric argument, right? Basically, this is what you saw in the original JL proof. Basically, what you said is, look, all the green balls combined, all the red balls combined are contained in a slightly larger ball of radius 1 plus epsilon over 2. So you have a bunch of balls, red balls, of radius epsilon over 2. They're disjoint. They're contained in a larger ball of radius 1 plus. So you have a bunch of radius epsilon over 2 balls that are disjoint containing a larger ball of radius 1 plus epsilon over 2. So just by comparing volumes, you can say there can't possibly be too many of these red balls. Otherwise, I would have too much volume. That wouldn't fit in the larger yellow circle. Right? This yellow circle is this yellow circle. That's guaranteed to contain all the red balls. So this has radius 1 plus epsilon over 2. So you know that this thing here has to be at most basically 1 plus epsilon over 2 over epsilon over 2 raised to the dimension. which is equal to kind of 1 plus, so what is this? 1 plus 2 over epsilon, I guess. Right? So the corollary is that this covering number, this entropy number, is always at most 1 plus 2 over epsilon to the dimension. So we're going to use that fact. Okay, good. Now you know enough preliminaries that we can actually do the lower bound. Questions about any of this? Okay.
Sorry, just a quick question.
Yeah.
The first inequality of the covering number to the packing number holds for any metric, right? Not just.
Yeah, that's true. Yep, any metric.
Okay.
Any normed space.
Well, does it need to be a norm?
Oh, does it need to be a norm? I guess you're right.
Like you just
I don't think.
Inequality.
Yeah, I guess you're right. Maybe that first inequality, I think, can be an arbitrary metric.
But then for the packing argument or for the volumetric argument, you need it to be a norm space.
That need to be a norm. That's right. Yeah.
Okay. Thanks.
Okay, so now the JL.
Sorry,
Yeah.
I'm still confused on what the entropy number is.
What you mean? What does it mean?
Yeah.
So we had the definition earlier of what an epsilon net is, right?
Yeah.
And the entropy number is just, like, so these red points here, that's an epsilon net, but I could just add a bunch of more points just unnecessarily. I would still have an epsilon net, right?
Okay.
You see here, I'm just adding more and more points. So the entropy number is just like, think of it as an optimization problem. Like, find me the smallest epsilon net of T. Okay. The size of the smallest epsilon net, that's the entropy number. Okay. So here, when I say that the entropy number is at most 1 plus 2 over epsilon to the D, what I'm saying is there always exists an epsilon net of size at most 1 plus 2 over epsilon to the D. If you're trying to cover the ball with, in its own norm. Okay. So good. So okay, we have 20 minutes left. So I mean, let's try and get to the meat, the proof. I think we have time. So the first observation is that if X contains 0, then and also let's say X contains 0 and all other points have unit norm, Euclidean norm. Then I claim that this is all Euclidean. Then I claim that F has distortion, 1 plus epsilon implies that for all x, y, and capital X, if you look at the dot product of f of x and f of y, it's going to be equal to the original dot product with an additive error of at most epsilon. So the proof of that, and I'm translated, f is translated so that f of 0 is 0. Right, so the point is, okay, so x contains 0. I can assume without loss of generality that f of 0 is 0 just by translation. If f has distortion 1 plus epsilon, it implies that it preserves dot products. Why is that true? That's true because if I look at x minus y, L2 norm squared, that's equal to, all norms from now on, unless I say otherwise, are Euclidean. That's equal to x squared plus y squared minus twice the dot product. Meanwhile, if I look at f of x minus f of y, L2 norm squared, that's equal to f of x squared plus f of y squared minus twice the dot product of f of x and f of y. And you know that because f because x contains 0 and f has low distortion, the distance from f of x to 0 is approximately the distance from x to 0, which is 1, because they all have unit norm. So f of x has norm roughly 1 plus epsilon, between 1 minus epsilon and 1 plus epsilon. So this is 1 plus or minus epsilon. This is also 1 plus or minus epsilon. This is 1. This is 1. This is equal to kind of 1 plus or minus epsilon times x minus y L2 norm squared. Okay. So if you just rearrange these things, basically what you get is that this implies that kind of f of x dotted with f of y is going to be at most like some epsilon plus some, plus or minus epsilon. So let's say, let me do it like this. The difference between this and the actual dot product is going to be at most an epsilon plus another, epsilon times the norm squared between x and y. But by triangle inequality, x minus y has norm at most 2. So x minus y squared has norm at most 4. So this is at most 6 epsilon, for example. Does that make sense? So preserving distances on unit norm vectors together with 0 implies you preserve dot products up to an additive O of epsilon. I don't want to keep drawing the 6 all the time, so let's just call this epsilon. Okay. So now what I'm going to do is I'm going to define.
What did other points mean in that observation?
X has endpoints, right? So like one of them is 0, and then the others are just the other points. Does that make sense? X is 0 with a plus a bunch of other points. And those other points all have unit norm. So the strategy is going to be as follows. I'm going to define a collection A of point sets such that if it's true that for all point sets, by the way, are going to be size n in RD. RD. If it's true that for all point sets in A, there exists an embedding F mapping X to Rm with distortion 1 plus epsilon for M, let's say much less than 0.001 log n over epsilon squared, so much better than the JL bound by some big constant factor, then there exists an injection G mapping the collection into a set of size smaller than the collection, which is a contradiction. Okay. So what's the assumption I made to arrive at this contradiction? I said, if for all x there exists this f, right? So since there's a contradiction, it must be the case that there is some x for which there is no such f. So there is a lower bound. Again, I don't know which x that is. I just know it's some x in the collection, but I don't know which one. Okay, so what is the collection going to be? Now let's, for a set S subset of D of size K, define, let's call it Y sub S to be the indicator vector of S divided by root T. That implies that, by root K, sorry. What I mean by that is if you look at YSI, this is going to either be 1 over root K if I is in S and 0 otherwise. Okay, and I'm going to set K to be something like 100 over epsilon squared, I think. Yeah, let's say 100 over epsilon squared. Now, what do I know? I know that basically dot products encode information. If I look at EI dotted with YS, this is either going to be 1 over root K or 0. I mean, right? EI dotted with YS is also known as YS sub I. So that's exactly as above. So 1 over root K, oh, and actually, so I think I want the 100 to be in the denominator. One over 100 epsilon squared. So EI dot YS is either going to be 10 epsilon if I is in S or 0 otherwise. Okay. So, if I had, if my F preserved dot products up to, plus or minus epsilon, that would give me something like kind of F of EI dotted with F of YS is either going to be like at least 9 epsilon if I is in S, or at most epsilon if I is not in S. So there's still a gap. And then I'm going to find my point set X. I'm going to look at point sets that look as follows. Imagine that like X, and actually, I slightly fibbed. It's not going to be a point set. It's going to be a sequence of points, a point sequence, possibly with repetition. So it's a tuple of points that looks like 0, E1 up to ED, together with like YS1, YS2 up to like YSN minus D minus 1. So it's a sequence of endpoints. And A is like this, the collection of all such X. So notice that the size of A is equal to basically, the first D plus 1 vectors are fixed. They're just 0 E1 up to ED. How many possibilities are there for YS? There are D choose K, because you have to tell me which things are going to be in S. So D choose K raised to the N minus D minus 1. Okay? That makes sense? So any injection of A into, say, like 0, 1 bit strings of length, S must have S being at least the logarithm of A, which is N minus D minus 1 times log of D choose K is roughly K times the log of D over K. Okay. Which is, basically, N times K. What is K? It's 1 over epsilon squared. N over epsilon squared times log of epsilon squared D. And for now, let me make the assumption. This assumption can be removed later. Let me make the assumption that D is exactly equal to N over log 1 over epsilon. We'll see where that comes in, and I'll say why that can be removed. That assumption can be removed. But then this becomes basically N over epsilon squared log of epsilon squared D. And let me also make the assumption that epsilon is much bigger than both 1 over root N and 1 over root D. Why? Why is that a reasonable assumption? Again, there's always an embedding into dimension N minus 1 with no distortion. There's always an embedding into dimension D, namely the identity map with no distortion. So how are you going to prove a 1 over epsilon squared lower bound if 1 over epsilon squared is bigger than N or D? You can't. So we're going to make the assumption that basically 1 over epsilon squared is much less than the min of N and D. Or in other words, epsilon is much bigger than the max of 1 over root N and 1 over root D. So then epsilon squared d, which is epsilon squared n over log 1 over epsilon, up to a constant is the same as log n. So this is basically the same as, the epsilon squared inside the log doesn't really matter much because it's so far away. This is basically, black and n here. Okay. So what have we shown? We've shown that if you inject into bit strings of length s, we need s to be basically at least up to a constant n over epsilon squared log n. And then what I'll show you is low distortion embedding exists into Rm for all x in the collection implies an injection into bit strings of length O of nm. So I'm going to show you that if every single one of these point sets has a low distortion embedding into m-dimensional space, that implies the existence of an injection into bit strings of length nm. So that implies that nm has to be at least up to a constant n over epsilon squared log n, which implies that m has to be at least 1 over epsilon squared log n. That's where our lower bound is going to come from.
And how did you get the n inside the log?
How do I get the what?
The n inside the log, that epsilon squared d.
Yeah, I had this inside the log, right? And then I made this assumption. And then I also made this assumption. So basically that, let's say I'm assuming that specifically, oops. Oh, did I lose my share? Okay. So specifically what I mean is like, say epsilon is bigger than 1 over n to the 0.49, for example. Right. Then epsilon squared n over log 1 over epsilon is still poly n. It's still n to the 0.01 or something. So log of n to the 0.01 is still omega log n. Does that make sense? Oh, hello?
Yeah.
So maybe we can, you ask me offline after, because since we're running out of time.
Yeah, sorry.
So good. So this is what I need to show. I need to, basically the name of the game now is showing this thing. How do I show this? So I want to kind of represent which points that I have. I want to represent which points that I have by some encoding of length nm. What do I know? I know that I have an embedding into dimension m. So why don't I make this my encoding? I'll just write down, I'll write down f of 0, I'll write down f of e1, I'll write down f of ed, and then I'll write down f of ys1, and I'll write down f of ysm minus t minus 1. Each one of these is an m-dimensional vector, so each one is m numbers. There are n of them, so that's nm numbers. So here's an encoding of length nm, right? And if I have this, I claim that this is enough. Having this is enough to recover. Well, first of all, I know what all the EIs are. What I don't know are the YSs. I don't know what the S's are. But I claim that if I have all these Fs, I can recover the S's because of this. Right? I can just take all the dot products between the EIs and the YSs. Whenever a dot product is bigger than 9 epsilon, I know that means I is in S. Whenever it's less than epsilon, I know that means I is not in S. So I can recover every single S just via the information from these dot products. Okay. So what's wrong with this? Why does this not work? Any takers? Anyone see a problem with this? So since we're running out of time, I'll just tell you. The problem is that these are nm numbers. Yes, I can decompress, and this is an injection because I can recover the information from this. The problem is I want to have an injection into a small set, specifically bit strings of length nm. F of 0 is not a bit string of length m. It's a real vector of length m. So the entries of f of 0 are real numbers. So, you know, my encoding length is not even finite because every single number here is a real number of infinite precision. So here's my first attempt at a fix, okay, which is I'll round each entry of, you know, so if each f of x to an integer, to the closest integer multiple of gamma, where gamma is going to be some small number. Think of gamma as like much, much smaller than epsilon even. And then now the point is, if I look at f of x dotted with f of y, now there's going to be some error, right? Because this is equal to the sum over all I of xi plus or minus gamma. When I round to the nearest multiple of gamma, I'm changing each entry by at most gamma, right? So xi plus or minus gamma times yi plus or minus gamma, which is equal to x dot y plus some error because of the gammas. And I'm not going to show it. I'm almost out of time, but you can show that if gamma is less than something like, I think, epsilon over root m, that implies that the error is at most epsilon in magnitude. Okay. So what does that mean? That means that, you know, now let's, you know, basically what I'm doing is I'm rounding these things, these f's, I'm taking that vector and I'm rounding it each entry-wise to multiples of gamma. So now if I look at f tilde ei and f tilde of ys, this thing is going to be at least 8 epsilon because I'm going to lose an epsilon. And here it's at most 2 epsilon. But there's still a gap. So I can still tell which case I'm in. So that I'm still golden. Okay. And so now this actually is a finite length encoding, right? Because I don't have real numbers anymore. You know, each entry of the real, you know, these are m-dimensional vectors, but each entry is a multiple of gamma. How many multiples of gamma are there between -1 and 1, right? Each entry of this vector is definitely going to be between -1 and 1. So, you know, there are only 2 over gamma possibilities for each entry. So the number of possibilities for any vector is at most roughly 2 over gamma to the mth power, right? So my encoding length is at most n times m times basically log of 1 over gamma. Right? The number of possibilities is 2 over gamma to the m. So to write down which possibility I have takes log that number of bits, which is m times log 1 over gamma. So now you get that nm log 1 over gamma has to be at least, you know, the same lower bound we had above, n over epsilon squared log n. And if you solve for m, you know, the n's cancel, you solve for m, basically what you're going to get at the end of the day is m is at least 1 over epsilon squared times log n over log 1 over epsilon plus log n. Okay, so, you know, it's not terrible. It's pretty close to no-go alone's lower bound, but no-go alone didn't have this term. So it's very slightly worse than no-go alone's lower bound. And now you stop, you know, okay, so we have only basically 30 seconds left. So here's what I'm going to do. I'm going to tell you a slightly better fix. And then on Monday, I'll tell you the final fix to get the optimal bound. And, you know, given what we've done so far, explaining that is going to take less than 5 minutes. But unfortunately, we're out of time. So here was the, you know, so the first fix was we're going to round each entry of the vectors to the nearest multiple of gamma. Okay. Now, what is that really doing? It's really taking an L infinity net of the L2 ball, right? I know that all of these f's, f of x is contained in the L2 ball of radius 1 plus epsilon or something, let's say almost radius 1. And I'm taking entries of that and rounding them to the nearest gamma net, to the nearest element of a gamma net under L infinity, right? L infinity, the L infinity distance between two vectors, the L infinity norm is just the magnitude of the largest entry, right? So I'm saying that, you know, I have x and I want to round it to x prime. such that for all I, xi minus x prime at position I is at most gamma in magnitude. So that's saying that I want to have an L infinity net of quality gamma. So the better fix actually is to round to an epsilon net in L2. Don't round to a gamma net in L infinity, round to an epsilon net in L2. Okay. So, and then I'm going to ask myself, okay, now what's the encoding length? Basically, for each one of these f of x's, I need to tell you which element of my epsilon net was the closest element to f of ei or to f of ys. How many bits does that take? Well, what vector is it in the epsilon net? Well, the epsilon net has size equal to the entropy number, right? The entropy number is the size of the smallest epsilon net. So how many bits does it take to tell you which element of the net I have? Log of the entropy number. Okay, so then what you get is basically like n times log of the entropy number is at least n over epsilon squared log n. And if you just solve for what the entropy number is, you're gonna get something like m is at least 1 over epsilon squared log n over log 1 over epsilon. So you're gonna get the same thing as before, but without this log n. In particular, this is exactly Nogel-Lohn's lower bound. But it's a completely different argument. His argument didn't go like this at all. And then you have to do one more kind of final clever trick to get rid of the log 1 over epsilon. And that's what I'm going to show you on Monday, because I'm out of time right now. But it's really not a big step it's not a big jump from what we've done. Okay, so I'm out of time. Let me end the recording and then take questions.